Hello team, this is Real World Audio, and we are continuing our quest on the measurement of distortion. And now this is a little bit of a sidetrack, and I'm going to show in this video the role of an output transformer in a single-ended triode amplifier. And here we go. Let's go back to the stereophile measurements and of the Yamamoto A08 amplifier, which is a single-ended triode amplifier. And Yamamoto, they make their own output transformers, and the Yamamoto output transformers are very high quality, extremely well made output transformers. And here we are very lucky because Stereophile has provided us square wave measurements at both 1 kilohertz and 10 kilohertz with the Yamamoto amplifier. And that's very important because if you recall, I have mentioned that the easiest frequency to reproduce by an audio amplifier is the 1 kilohertz frequency. If we go, and they rarely publish this frequency because it's relatively easy to reproduce. And if we go higher than that, then it becomes harder to reproduce that frequency. And if we go lower than that, it also becomes harder to reproduce. Talking about vacuum tube amplifiers, it's becoming harder when you go higher in the frequency because of the capacitance of the output transformer. So that's why when we go from 1 kilohertz, you see the square waves look pretty much almost like a perfect square. And when we go to 10 kilohertz, now we see that the straightness becomes more slopy, and at the end we see this rounding in the shoulder, and that's because of the added capacitance of the output transformer, so mainly the interwinding capacitance, which is the capacitance between the primary and the secondary coils, and also because of the core saturation. So the transformer core, as you try to give it higher and higher signal levels, it will start to saturate. So we will see some dynamic compression in it, and this sloping is indicative of that compression happening, and those tiny squiggles are indicative of the capacitance between the primary and secondary windings. So you see that at 10 kilohertz we are not seeing square waves anymore, perfect squares, but they will slowly turn into triangle waves. So the perfect square, if you look at this was the perfect square, so now it's trying to like getting bendy like that, and it will get more bendy and bendy, and when we look at 200 kilohertz, they will become sawtooth waves, basically triangles. So the squares will change shape into a wavy form first, and then basically like a sawtooth wave. And that's because of the limitation of the output transformer. And now if you have a good output transformer, then this change occurs at higher frequencies and not to such a big degree. And when you see a wave like this at 10 kilohertz, it shows that we are dealing with an extremely good output transformer. Sadly, the other end of the spectrum is not shown here, so we do not see what happens to the square wave when we go lower than 1 kilohertz. When we drop down to 200 hertz, essentially the square waves will stay just like the same. But when we hit 100 hertz and we go lower, then basically what we would see if we would look at it on the oscilloscope is this, the bottom of the square wave would start to like curve up. and you would start to see these drooping down. And here we are at 1 kilohertz, and we are down to 100 hertz, same thing. And then as you go down to 80 hertz, 70 hertz, 40, 20 hertz, 10 hertz. So at 10 hertz, probably they would be at this slope. And there the problem is because of the inductance, because we are running out of inductance. So when you go at the high end of the spectrum at 20 kilohertz, 50, so for the Yamamoto, we would hit the high frequency peak around 50 kilohertz. Then it's the capacitance of the output transformer which is limiting. And when we go to the low end response towards 10 hertz, 20 hertz, 5 hertz, then it's the lack of inductance, the decreasing inductance that becomes the limit of an output transformer. And to have an output transformer that has enough inductance and at the same time has very low interwinding capacitance, that's truly requires extremely high level of knowledge and practice, because it's not enough to know things. You have to be able to implement it, because winding output transformers is not something easy. It's very, very complex. So thank you everyone for tuning in, and I hope now we know a little bit more on how square waves look for a single-ended triode amplifier. And if you have one at home and you have hooked it up to a signal generator and an oscilloscope, then when you do a frequency sweep, so you go, let's say, from 10 hertz to 100 kilohertz, then now this is it, what you will expect to see. And I can tell you, you will see something similar with push-pull triode amplifiers as well. So the changes when you go low in frequency, so this drooping will be true for a push-pull amplifier, and your square waves turning into sawtooth waves at the high frequencies, that will happen with push-pull as well. And thank you for tuning in. Please like, subscribe. Bye-bye.